Hello, I'm Ralph Gable of the Electronics for the Inquisitive Experimenter YouTube channel. In the last video, I introduced the basic model that we use for circuit analysis of the bipolar junction transistor, along with the assumptions that we make about them. If you missed that one, I recommend that you watch it, as it is the foundation of what we're going to be doing in this video. I've put a link up in the corner to that video for your convenience. In this video, I'm going to step through the design and analysis of a common emitter circuit to get its DC operating point into the active region. This is referred to as the quiescent operating point of a transistor circuit. I have provided a go-along with the video document for you, which has the whole process in it, along with some extra equations for input impedance, output impedance, and voltage gain. You will find a link to this document in the description. Now, in this analysis that we're going to be doing today, I will leverage the model of the transistor operation that I presented in the previous video. I will also have to use Kirchhoff's voltage law. I have a video on that very topic. If you're interested in getting a leg up on it before diving in here, I put a link to that video up in the corner for you. After we work through the calculation of component values, I will go to the bench to see how these values actually work using a 2N3904 transistor that I randomly picked out of my collection. We will have to do a little reverse engineering to determine what to expect from our bench experiment, being that the actual resistor values that I brought out of my junk box will not exactly match the calculated values from our design analysis. I have a very important additional note that you must absolutely remember when creating a transistor circuit that doesn't live by itself. Anything that is connected to the input or to the output of the circuit becomes part of the circuit. They become either current sources or current sinks that can and will change the operation of the circuit, so pay attention to this. Now, if you have questions or comments, please feel free to add a comment to this video. If you find this video helpful, please click on the like and don't forget to subscribe. The purpose of this exercise is to set the operating point of the transistor within its linear active region. So what does this circuit look like? We are talking about a common emitter configuration which has the following characteristics. It has a medium to high input impedance. It has a medium to high output impedance. It provides both voltage and current gain. It is an inverting amplifier, which means that its output is phase shifted by 180 degrees. In other words, when the input goes low, the output goes high. As a common emitter circuit, the emitter is connected to both the input and the output. This is the ground point of the circuit. We need a power supply. For this demonstration, our power supply is set to 12 volts. This is VCC in our schematic. With this power supply voltage, we want to set our collector-emitter voltage, or VCE, to half the power supply voltage to give us as much voltage swing as possible. This means we're looking for a collector-emitter voltage of 6 volts. To accomplish this, there needs to be a resistor between the power supply and the collector to drop the power supply voltage to the desired VCE of 6 volts. I will call this resistor RC. We are using a 2N3904 transistor. We need to know its DC current gain, or beta, so we will take a look at the data sheet. According to the data sheet, the H sub FE can be from 100 to 300 at a collector current of 10 milliamps. I'm going to choose a value midway between these two, so I'm going to choose to use an H sub FE, or beta, of 200. Now, with a little help from the data sheet and while picking a number out of the air, our desired collector current operating point is going to be 10 milliamps. This is IC. Using the basic model, The base emitter voltage VBE will never rise above 0.7 volts, so our input needs some sort of resistor to act as a current limiting to the base. The other side of this resistor is connected to the power supply voltage source. This provides the bias current to the base. I will call this resistor RB. Now that we have our circuit, what are we trying to accomplish? We want to calculate the needed collector resistor and the needed base resistor to achieve a collector-emitter voltage of 6 volts with a collector current of 10 milliamps using our 2N3904 transistor with a DC current gain of 200. Now, on to the analysis. If we're going to be able to calculate the value of the collector resistor, we need to calculate the voltage drop across the collector resistor. To get at this, we're going to use Kirchhoff's voltage law, which states that the sum of the voltages around any loop must be equal to 0. I will be using the loop starting at the negative side of the power supply. Going from the negative side of the power supply to the positive side of the power supply, well, this is a positive change. We are now moving away from the positive terminal of the power supply through the collector resistor, so this is a negative change. We continue to move away from the positive terminal and toward the negative terminal of the power supply as we drop through the collector to the emitter of the transistor. This is also a negative change. Now that we've arrived at the emitter, we're back at the negative side of the power supply where we started via the ground connection. Now, let's write this trip in the form of an equation. This would give us the power supply voltage, or VCC, minus the voltage across the collector resistor, or VRC, minus the voltage between the collector and the emitter of the transistor, or VCE, is equal to 0. Now, because we want to know VRC, I'm going to add VRC to both sides, which gives us the voltage across the collector resistor, VRC, is equal to the power supply voltage minus the voltage between the collector and emitter of the transistor. So what do we know at this point? We know that the power supply voltage, or VCC, is 12 volts, and the target collector-emitter voltage, VCE, is 6 volts. So the voltage across the collector resistor is equal to 12 volts minus 6 volts, which gives us a voltage across the collector resistor of 6 volts. Now remember, our goal is to calculate the value of the collector resistor. Ohm's law tells us that the value of the collector resistor is equal to the voltage across it divided by the current through it. We already know the voltage across the collector resistor, but what else do we know? Well, from our design definition, we know the desired collector current is 10 milliamps. Putting all of this into our Ohm's law equation, we have the value of the collector resistor is equal to 6 volts divided by 10 milliamperes. This gives us a collector resistor value of 600 ohms. So we've achieved our first objective. We have defined the value of the collector resistor. Now, let's turn our attention to the base circuit. Well, according to Ohm's law, the value of the base resistor is equal to the voltage across it divided by the current through it. This means that we have to determine what the voltage across the base resistor is and what the current through the base resistor is. We begin with the voltage across the base resistor. Like with the collector, we will use Kirchhoff's voltage law, only using the loop around the base circuit this time. Like before, we start at the negative terminal of the power supply and move to the positive terminal. This is a positive change. We come to the base resistor and we begin to move away from the positive side of the power supply toward the negative side. So this is a voltage drop across the resistor. It is a negative change in voltage. We come to the base of the transistor. Moving from the base of the transistor toward the emitter, we arrive once again at the power supply's negative terminal. This base emitter voltage is yet another voltage drop, a negative voltage change. Now, let's write this trip in the form of an equation. This would give us the power supply voltage, or VCC, minus the voltage across the base resistor, VRB, minus the voltage across the base emitter junction of the transistor, VBE, equals 0. Because we're interested in the voltage across the base resistor, VRB, we add VRB to both sides, and we get the voltage across the base resistor is equal to the power supply voltage minus the voltage across the base emitter junction of the transistor. So at this point, what do we know? Well, we know our power supply VCC is 12 volts, and we know that the base emitter voltage is 0.7 volts per our model. So substituting these values in our equation, we get the voltage across the base resistor is equal to 12 volts minus 0.7 volts. So the voltage across our base resistor is 11.3 volts. Now that we know the voltage across the base resistor, we need to determine the current through it. So we ask, how can we figure out what the base current is? What else do we know? Well, we know that collector current is equal to the base current times beta, the DC current gain of the transistor. If we divide both sides by beta to get the base current all alone on one side, we get the base current is equal to the collector current divided by beta. So at this point, again, what do we know? We know that beta is essentially the same as H sub Fe, which we decided to be 200 by our design assumptions. And we also know that the desired collector current is 10 milliamps per our design goals. So putting all this in our equation, this gives us a base current is equal to 10 milliamps divided by 200, which means that we have a base current of 50 microamps. Now we get to go back to where we started with Ohm's law, and we now know that the voltage across the base resistor is 11.3 volts, and the current through the base resistor is 50 microamps. We put these values into our equation, and we get the value the base resistor is equal to 11.3 volts divided by 50 microamps, which gives us a base resistor value of 226 k ohms. So, with our second objective achieved, we have the circuit fully defined. Now I'm going to go to the junk box and see if I can put this together to see if it really works. Well, I have successfully engineered the design of our common emitter circuit. Well, to put it on the bench, I randomly grabbed a 2N3904 transistor from my collection of transistors, and I found a 604 ohm resistor, which actually measures 606 ohms to use for the collector resistor. Unfortunately, the closest resistor I could find to our calculated 226 k ohm resistor for the base resistor was a 221 k ohm resistor, which actually measures 223.8 k ohms. Well, these are not exactly the values I calculated, so I have to ask the question, given these values, what collector-emitter voltage can I expect? Now we get to reverse engineer our circuit. Think of this as a circuit somewhere that you came across and want to know what it does. We need to start with the base because, well, we need to know the base current to find the collector current. We know Ohm's law tells us that the current through the base resistor is equal to the voltage across the base resistor divided by the value of the base resistor. Now, we already know the value of the base resistor, so we have to determine the voltage across the base resistor. To do this, we get to visit the world of Kirchhoff's voltage law again. We will reuse the loop through the base circuit. Now, because I want to know the voltage across the base resistor, VRB, I will add VRB to both sides, and this isolates it to the other side of the equal sign, kind of like this. VRB is equal to the power supply voltage minus the voltage across the base emitter junction. And we know that the power supply, VCC, is 12 volts, and we know the voltage across the base emitter junction, VBE, is 0.7 volts per our model. So substituting these values in our equation, we get the voltage across the base resistor is equal to 12 volts minus 0.7 volts, which gives us the voltage across the base resistor of 11.3 volts. Now, this looks pretty familiar. The voltage across the base resistor actually hasn't changed from before. But what has changed is the current through the base resistor, because the value of the base resistor has changed. So the question is, what is the base current? We go back to our Ohm's law equation. What do we know? Well, we just calculated the voltage across it is 11.3 volts. We know the value of it is 223.8 k ohms, well, because we measured it. Putting these values into our Ohm's law equation, we get the current through the base resistor, or the base current, is equal to 11.3 volts divided by 223.8 k ohms. So the base current is 50.5 microamps. Now we know the base current. And with this, we can turn our attention to the collector side of the circuit. Well, we need to figure out what the collector voltage is going to be. To get the collector voltage, we have to go back to the Kirchhoff's voltage equation that we used for the collector loop previously. Now we're interested in the collector-emitter voltage VCE, so I add VCE to both sides of this equation to get it by itself on the other side of the equal sign. This gives us VCE is equal to the power supply voltage minus the voltage across the resistor. Unfortunately, the only thing that we know at this point is the power supply voltage. We need to calculate the voltage across the collector resistor. So we drop back to Ohm's law, which tells us that the voltage across the collector resistor is equal to the current through it times the value of it. Again, we're faced with only knowing one thing, the value of the collector resistor. So we have to ask, how can we find the current through the collector resistor? Well, we know the collector current is equal to the base current times the DC current gain. And, well, we know that we have a DC current gain of 200, and we know that we have a base current of 50.5 microamps. So the collector current is equal to 50.5 microamps times 200. So we have discovered that we have a collector current of 10.1 milliamps. Oh, fantastic. Now we can calculate the voltage across the collector resistor using our Ohm's law equation. So with a collector current of 10.1 milliamps and a collector resistor value of 606 ohms, this gives us the voltage across the collector resistor of 10.1 milliamps times 606 ohms, which gives us a voltage of 6.12 volts. Well, now that we know the voltage across the collector resistor, we can back up once again to our Kirchhoff's voltage equation. And now we know that the power supply voltage is 12 volts. We know that the voltage across the collector resistor, VRC, is 6.12 volts. Substituting these values into our equation, we have the collector-emitter voltage is equal to 12 volts minus 6.12 volts, which means that we can expect the collector-emitter voltage to be 5.88 volts. Now, let's go to the bench and see what we're actually reading. So, here's my little setup. Notice the voltage between the collector and the emitter is 5.86 volts. We were expecting 5.88 volts. Not too shabby. But reality hits. The calculation of these resistor values and the success of our bench experiment all depended upon the actual real-world transistor having a DC current gain of 200. In our case, I just happened to choose a transistor that had a DC current gain of around 200 in my random pick from my junk box. But what happens if the transistor we happen to get doesn't have a DC current gain of 200? I mean, the data sheet says it could be as low as 100, which is half of what we used here. But it also says that it could be as high as 300. That's 50% higher than what we used here. What happens then? Well, let's try a few other random choices of transistors from my junk box. I get 4.69 volts for the first one, 5.97 volts for the second, the third gives us 6.42 volts, and lastly, the fourth yields 5.36 volts. Each transistor has a different DC current gain and base emitter voltage, and so the collector emitter voltage varies all over the place depending upon which transistor we use. So what do we do about that? That answer lay in a video to come on a beta stable design. This design changes just two things in the circuit that makes all the difference in the world, and when this is released, you'll find a link to it up in the corner up here just for you. Well, I have to repeat my very important additional note that you absolutely must remember when creating a transistor circuit that doesn't live by itself. Anything that you connect to the input or to the output of the circuit becomes part of the circuit. They either become a current source or a current sink that can and will change the operation of the circuit. So pay attention to this. We have completed the basic circuit analysis for the common-emitter transistor circuit. In the next video, I'm going to cover the common collector transistor circuit. If you found this video helpful, please click on the like and subscribe to the channel. Thank you so much for watching. Until next time, Toodle-Oots.